We've already discussed in this course that the main purpose of statistics is really the study of variation. So now we'll start getting a little deeper into that particular topic. So in this lesson, we'll only try to understand what we mean by variation and how do we quantify variation and how do we compute it using R. Okay, so for example, there is a data set called SAT, a data frame. And within that, we see that there are two, at least we are looking at two columns, state and the average SAT score for that state. Okay, and then clearly we are seeing that there is variation in the states and there is variation in the SAT score, in the sense that not all the scores are the same. Similarly, there is this Anthro F data frame, and there you've got the neck measurements of various people, and of course we see variation in the neck measurements. And then finally, there's the births 2022 data frame, in which among several columns there is a column called weight, and the weight column also displays variation. Okay, so there's variation, and in statistics we study the variation, meaning how much variation exists and how is the variation related to the variation in other variables. In other words, explaining the variation, and also figuring out how much of the variation remains unexplained. Okay, so that's really the idea that we want to get across in this particular lecture. Okay, so statistical thinking is the accounting for variation in the context of what remains unaccounted for. Okay, so we are interested in both what variation is accounted for and also what variation is not accounted for. And we'll make all of these very clear as we go forward. Okay, so we'll be learning how to measure variation, how to account for the variation or explain the variation, and also to measure what remains unexplained or unaccounted for. Okay, let's start with a very simple example. Consider the four pairs of numbers below. The first pair is the two numbers 2020, and the second pair is 2025, 1030, and 1040. Now obviously, if you look at these two numbers 2020, there is no variation. Both the numbers are exactly the same. If you look at the numbers 2025, there is variation. One is 20, the other is 25, so both are not the same. And then you look at the numbers, so therefore you can say that the variation in the pair 2020 is less than the variation in the pair 2025. 2025 has more variation than 2020. Okay. Now if we continue further, we find that the variation in 1030 is even more than in 2025, because 20 and 25 are kind of close to each other. 10 and 30 are further apart. So we say that the variation in 1030 is more than the variation in 2025. And finally, the variation in 1040 is even more than that in 1030, because the numbers are much further apart. Okay, so not only are we trying to say that there is variation in the values of a particular variable, we also want to say to what extent is the variation there, is one variation greater than the other, and also we will later on shortly go and see how we can assign an actual number to this variation. Okay, so clearly there is the quantity of variation, and we can say that some variations are more than other variations. There is the intuition, and then of course there is the actual calculation. Okay, so the intuition for variation is, well, how can we express the variation as a single number? Okay, so you've got these four pairs. Okay, one way to express the variation between the numbers is to simply say what is the difference. Okay, so clearly the difference here is 0, that is 5, that is 20, that is 30, and therefore we can say, well, the variation is clearly more in this than this, and this than this, and that than that. Okay, now in statistics, it is common to not just compute the variation as the difference, but to treat the variation as the square of the difference. Okay, so we have taken the square of each of these numbers. Okay, why is that? Because often when you calculate differences, some may be positive, some may be negative, and therefore when you square them, the negatives go away and all become positive numbers. And there's also another deeper statistical reason why we are interested in the square than in the absolute difference. Okay, now as an actual measure of variation, it is in statistics, it is basically the square of the difference divided by 2. Okay, so that's actually how we compute the variation in statistics. Of course, here the variation is only 2 numbers. In general, you can have more numbers, and we'll see those later. Okay, so we have taken the square of the difference between the 2 numbers and then divided it by 2 to get this variation. So clearly now you can see that this variation is more than this, which is more than this, which is more than that. And this is how we measure variation in statistics. Okay, so the general principle is, suppose you have 3 numbers, then take all possible pairs of numbers and find the average of the squared deviation and divide it by 2. Okay, so in the earlier case there was only 1 pair of numbers. Okay, so we didn't have to do this. If you have more than 2, then let's say we have these 3 numbers. Okay, we are going to consider every pair of numbers, so we'll consider 2, 8, 2, 4, 8, 4. Okay, so with 2, 8, the difference is 6, the squared difference is 36. With 2, 4, the difference is 2, the squared difference is 4. And finally, with 8, 4, the difference is 4, and the squared difference is 16. Okay, so in this case, the difference was 2 and the squared difference was 4. Okay, so the total of the squared deviation is 56, 36 plus 4, 40 plus 16, 56. And the average of those is 18.66. Okay, so we are taking the squared deviation, finding the average, and then dividing the average by 2, 9.33. Well, that's the variation in these 3 numbers. Okay, the name given is variance. So the variance of these 3 numbers is 9.33333. So what we are doing is, we are taking every possible pair of numbers. With 3 numbers, there are only 3 possible pairs. Okay, we are taking every possible pair of numbers, finding the squared deviation, squared difference between those numbers, finding the average of all of those numbers, the average squared deviation, and then dividing it by 2 to calculate the variance. Of course, going forward, you don't have to calculate the variance by hand. R will calculate it for you. But you can see how this is really a compounded measure of the variation among a set of numbers. Okay, if you had 4 numbers, then there would be many pairs of numbers, not just 4, right? Because you have 1, 2, 1, 3, 1, 4, that is 3, and then 2, 3, 2, 4, that is plus 2, 5, and then 3, 4, 6. So if you have 4 numbers, there would be 6 pairs. And again, we'll do the same thing. Calculate the squared difference, take the average, divide it by 2. Okay, and that is the variance. Okay, let's take an example of 4 numbers. Well, we take the numbers 2, 8, 4, 10. Okay, so again 2, 8, 2, 4, 2, 10, and then 8, 4, 8, 10, and then 4, 10. 6 different pairs. And for every pair, we have done the same thing. Taken the squared differences, averaged the squared difference, divided by 2. That's the variance. Okay. There are other formulas for calculating the variance, but this is the general idea, and you really don't need to know any of the other formulas for calculating variance. Okay. So how do you calculate the variance using R? Well, just use the var function. So Galton is a data frame, and then we use summarize, of course. Remember, when we wanted to calculate the average, we used summarize. Similarly, we want to calculate the variance, we use the function var. So we say var height, and the outcome comes as var height is 12.8373. Okay, that's the variance of the data in the column height. Okay, there are many rows in the data frame Galton, 800 I think. So out of all those 800 heights, the variation or variance is 12.8373. Similarly, in the births data frame, we want to find the variance of weight. So we say births 2022, summarize var weight. This time I use na.rm equals true because there are some missing values in the column weight. So we wanted to compute the variance while ignoring the missing values. And that comes out as a large number because this is a much larger data set. This is 20,000 rows. So obviously, as the number of rows increases, the variance could increase, right? Because there would be some numbers which have large differences, and so the variance will increase. Okay, so what are the units of variance? Well, since we are squaring the numbers, right? Remember, notice that here for every number, so if you recall, when we calculated the variance by hand, we found the differences, squared them, took the average and divided by 2. Okay, so the basic idea, the values that you have are squares of whatever item you are computing. So in this case, the heights were measured in inches, and therefore the variance of height is squared inches squared. Okay, similarly, the variance of weight would be gram square because the unit is grams. Okay, so we don't like, we can't interpret squared units that well. So typically what we do is we take the square root of the variance, and that is called the standard deviation. Okay, in fact, standard deviation is considered as a good measure of the spread of data. Okay, so in this case, the standard deviation of heights would be 3.58 inches this time. It's in the same unit as whatever you're measuring. It's not in square inches, right? So standard deviation makes a little more sense to us. Like for example, suppose I say the average height is something, and then I say the standard deviation of height is something that is also in inches, the average height is also in inches. So we get a good idea of the spread of data when it's measured in standard deviation, okay, rather than as variance. Okay. Similarly, the standard deviation of weight is in grams, 580 grams. Okay. So usually we use standard deviation as a common measure of spread of data as well. Okay. Variance is also used. Both of these are used, and you will encounter standard deviation quite a lot.